Okay, so we're just to finish up with this one. So we have our probability here that that our random variable x is equal to 3 is our 5 choose 3 times 3 successes, right? Success to the power of 3 and failure to the power of 2. Once you work that out, right, because 5 choose 3 is 10, and then we multiply that by 0.5 to the 3, 0.5 to the 2, we end up with this answer, right? So 0.3125, which is fairly likely, which makes sense because throwing 3 heads out of 5 is a fairly common occurrence. So to go back to our formula here for a second, let's look at the formula closer one more time. I want you to make this change to the formula. I want you to change that where it says small x, and make sure you write capital X equals x. And I know this seems odd, right? People remember, they forget the difference between the capital and the lowercase. The capital X represents the random variable. It represents all the different values that are possible in the experiment. What this formula tells us is the probability that the random variable x is equal to a particular x is given by this formula. So for instance, what we did right over here, the probability that our capital X is equal to 3 is given by the formula, right? In this case, our lowercase x was a 3, right? But some people get mixed up with this, so make sure you take a minute to think this through. The capital X represents all the different outcomes of the experiment. What this equation tells us is the probability that that capital X has the specific value that we pick for lowercase x, which is what we're about to do now. We'll go through an example of this one. So again, here we are, probability distribution, number of heads, tossing a coin 5 times. Create the probability histogram to illustrate the results. Okay, so success is defined as tossing a head. N represents 5, which is the number of trials. It says that in the question. X represents, we will have to go through one at a time, each value, or 0, 1, 2, 3, 4, 5. X is equal to the number of successes. Okay. We're going to have to do them one at a time, though, obviously, because we're looking at a number of different cases. P is the probability of success, which is 0.5. Q is the probability of failure, which in this case is 0.5, because, in other words, it's tossing a tail, whereas this one is tossing a head. Okay, so this is all the variables we need to solve this problem, and we just need to use the formula now, basically, to practice. So looking here, number of heads, we could have 0, 1, 2, 3, 4, 5. Probability wise, we're looking at 5 choose 0. Right? 5 choose 0, right? We have 0 successes times success to the power of 0 times failure to the power of 5. Basically, we're looking for 5 failures, right? Now we know that 5 choose 0 is 1. Anything to the power of 0 is also 1, and 5 to the 5 is 0.3.125. Ergo, the probability of throwing 0 heads, p of 0, p that x equals 0, is given by 0.3125. Okay, that would be our first answer here. The second one, we're looking at 5 choose 1 times 0.5 power of 1, 0.5 to the power of 4. Now, what you're going to notice here is that when it is 50-50, a lot of our work is very simple, because 0.5 to the 0 times 0.5 to the 5, this part of the equation is actually identical to this part. You can go ahead on your calculator and try it, but 0.5 to the 1 times 0.5 to the 4 is also going to be 0.3 decimal, 0.0 decimal, 0.03125. Okay, when we multiply that by 5, we just end up with 0.1515625. Okay, so that completes our number of probability, or our, the possibility of throwing heads. 1 head, sorry. To throw 2 heads, we have 5 choose 2 times 0.5 to the 2 times 0.5 to the 3. And again, we should get the hang of it by now. 5 choose 2 is 10. And again, our decimal part is going to be the same because it's 50-50 chance. And this is the same answer that we got when we were just going through the example before, right? The same decimal, 0.3125, which is here. Now, a nice thing about 50-50 questions is throwing 2 heads out of 5 is the same as throwing 3 heads out of 5, because it's going to be 5 choose 3. And remember from Pascal's triangle, right, that it's symmetrical. And so, you know, here we get the same thing as the one above it, which we'll just quickly do the rest of these, and the one above that, and the one above that. And if we're at all unsure that this is right, we should add them all up and double check that the probability is 1, right? So you can take a second now, you can add them all up, right? So this one plus these two. So these two make 0.625, and these ones make, you know, let's just quickly, we'll just have the computer do this. Okay, so we're going to take sorry, 0.03125, okay? We have 0.15625, and we have 0.3125. So we're going to have C plus D plus E, right? Those three things we just did, times 2. And we find that it is 1. And it's not just rounding to 1, it is at 15 decimal places, still equal to exactly 1, because this distribution that we created is perfect, right? It's theoretical, it doesn't make any mistakes. The probability histogram, okay? The probability histogram looks exactly like this. Let's just take a quick look at this picture. Get rid of this. We know our probability here was 50%. Get rid of this. And we had 5 trials. Okay. Now in GeoGebra, okay, you're gonna have to just bear with me that it has to be centered on the 0, but you actually don't really want it on the 0. You want it moved over a little bit. Remember, don't worry about your graph starting at 0, 0 when you're doing these ones. Even if it's a negative number like we were doing with the deal or no deal, you just push it over to the side, okay? So here you can see what your histogram looks like. It's symmetrical because this probability was 50-50. Throwing 2 heads or 3 heads was very likely, right? It was above 30%. Throwing 1 head or 4 heads is less likely, right? It's about 16%. And getting no heads or getting all heads is quite unlikely as well, right? It's 3%. So our probability histogram here is a perfectly symmetrical bar graph, right? Histogram, where it's mirrored, right? 0 is mirrored with 5, 1 is mirrored with 4, and 3 is mirrored with 2. And this, of course, corresponds to the fact that, you know, we saw this symmetry in our answers. And again, this works for a 50-50 histogram. But, you know, you can see here, if I change the probability and don't make it 50-50, well, it changes the scale, right? All of a sudden now it's not symmetrical. We have you know, it's distorted in one direction or another, because we might expect to find more successes if probability of success, like it is in this example, is a bit higher, right? 0.65. If we make the probability of success very low, then now, you know, how many successes do we see? A lot of zeros, only you know, a lot of ones, a couple twos, and virtually no 3s or 4s, right? So in a 50-50 histogram, it looks perfect. So again, good communication question, right? If the probability distribution is symmetrical, right, what can you conclude about the probability? And we could say the probability of success has got to be 50%, right, in order to produce this perfect symmetrical picture, because as soon as we move the probability in either direction, the symmetry is gone. Okay, let's try a more difficult problem. In a manufacturing process, it's estimated that 0.1% of the products are defective. A client places an order for 25 of these products. What is the probability that 3 of them are defective, none of them are defective, at least 1 or 2 or less? Okay, so again, we're looking at a variety of options here. let's you know, let's work out how these would go. So first things first, when you're doing a binomial distribution, you need to know 4 things: n, x, q, or sorry, p, q. Okay, we need to know those 4 things every time. This is how you should start every single question. Write down those 4 things and say what they are. In this case, the client's ordering 25 products. We have 25, therefore, the trials. Remember, these are independent, right? Because the products are defective. One product being defective has nothing to do with the next product being defective. So they're independent trials. And remember, the binomial distribution only works for independent trials. If there's a suggestion that it's not independent, you can't use the binomial. Okay? So 25, we're doing 25 trials. X in this case is going to be X is going to be equal to 3 because we have 3 defective parts. We're going to define a defective part as a success here, which you don't have to do, but you know, just to make it simple, we'll do it like that way. Q then would equal 0.999. Okay. So this is our P and Q, right? Remember, you know, keep in mind P plus Q is equal to 1, right? Always, which we can always use to our advantage. Now, to solve this one, right? To solve this one, what we're going to do is we're going to use our same old formula as before, right? NCX times P to the X times Q to the N minus X. Okay, and now all we're doing is just going to fill in the dots. 25, choose 3. I want 3 defective parts, so out of my 25, I want 3 of them to be defective, times the probability of a defective part, which is 0.001, to the power of 3, times 0.999 to the power of 22. Okay, and that is how we're going to calculate the probability that, let's just do this right, sorry, probability that X is equal to 3. Okay, big X, right? NCX and so on, and we work this out and solve it. So you know, to calculate that, and we'll go here. So 25 choose 3 is let's quickly get a sheet here. Okay. So let's go with, you know, we'll just do it. This will probably make it a bit easier for us. N is equal to 25. Q is equal to 0.999. X is equal to 3. P is equal to 0.001. GeoGebra is doing some rounding here, so let's correct this. I'll round it to 4 decimal places, okay? I can't use X either because it thinks that that's a straight line, so let's call it S for success. Okay, so our formula here is always the same. This just doesn't want to cooperate. We have, let's see if this works. And choose X times P to the X, P to the X, Q, and minus X. Okay, so it's always going to be that is always our equation. And remember, this is the probability capital X is equal to a given lowercase x. Okay, and we're going to do this by doing n factorial divided by so this is just the NCR part. So 3 factorial divided by 22 factorial. Sorry, let's do this correctly. S factorial divided by n minus s factorial. Okay, then we're going to do s, which is our success, to the power of p to the power of s times q to the power of n minus s. Okay, and GeoGebra is giving us a value of 0 for this. This is because, again, rounding wise, it's a bit small. Probability is 0.0000225. Okay, so extraordinarily small. And that should make sense to us because we're looking here, remember, at the probability that 3 parts are defective